All right, so now let's take a look at section 4.1 and look at the concept of an inverse function. So you'll remember from previous sections, we define a function. Here we have one illustration of a function. Note that every value in the domain of the function maps to an element in the range. So here you're saying, okay, there's something about A and W that has them paired together. There's some relationship between these two, and some relationship between B and X, C and Y, and D and Z. And here we see relationships among all of our elements in the first set and all of our elements in the second set. Likewise here. But just because you have a relationship between elements of a set does not mean that it's necessarily a function. Remember that the requirement for a function is that for every first element in our pair, you should only have it paired to a single element in the second set. Or in other words, once you say A in the domain is paired with W in the range, it shouldn't be paired with anything else. All right? So here we have an illustration of a function, whereas here we see an illustration of something that is not a function. All right? You have your domain, you have your range. This one, notice that A is tied to W, but here B is tied to both X and Y. And so if you wrote these out as ordered pairs, you would see something like AW, which is fine, but then you'd see BX and also BY. And so you would have two elements in your set here which have the same first entry. And so that would violate the definition of a function. Likewise over here we have a problem where here this B is tied to both X and Y. So here this would be a function. This would not be a function, and likewise here this would not be a function. Well, now there's one other consideration that we're going to be looking at in this section, and that is, okay, this might be a function. Is it reversible? What do you mean, is it reversible? Well, consider an illustration that looks like this. Let's say we had A, B, C, D, X, Y, Z. Okay? So now, let's say I had these sets of pairs. Now, is that a function? The answer is yes, this is a function. It would have this as its domain, and it would have this as its range, and this is in fact the function. If you write it out as a set of ordered pairs, you have AX, you'd have BY, you'd have CY, and you'd have DZ, which is fine. No distinct ordered pair has the same first entry. All right, here, yeah, the second entry is the same, but we don't care. The first entry is different for all of them, so yes, this is a function. Okay? So now, we have two examples of things that are functions and two examples of things that are not. All right, well, if they're not functions, then we're not going to worry about them in this section. Let's take a look at these. Both of these are functions, but notice that for this one, I could go in reverse. Meaning, if I tell you, if my first entry is A, what is my second entry? Well, it's W. If my first entry is B, my second entry is X. C pairs with Y, and D pairs with Z. But if I ask you to go backwards, you could do that as well. If I start with Z from my range, what did that tie to in the domain? Well, that was D. If you start with Y, that pairs with C, X pairs with B, and W pairs with A. You couldn't do that over here. Because notice, if I say, okay, I have a value from my range, which is an X, that's paired with an A. But if I say Y from the range, what is that paired with in the domain? Well, we don't know. It could pair with both B and C. When we talk about the inverse of a function, we mean exactly this. Can we go backwards? A function normally takes something from your domain and ties it to something in your range. An inverse would take that relationship and flip it. You would start with the element that's normally in your range and try to go back to the element in your domain. If you can't do that, if you don't have a way of reversing the relationship, then yes, they may be a function, but it's not invertible. So here we're defining is a one-to-one function. So let's take a definition. Let's begin with a function. Let f of x be a function. All right, so here we're not considering anything that's not a function. All right, we're only considering things that are. So let f of x be a function if for every a and b in the domain of the function f, we have that a not equal to b implies f at a is not equal to f at b, then f is called a one-to-one function. Okay. So let's talk about what that means a little bit more explicitly with an example. Now there's a couple of ways to tell whether or not a function is one-to-one, and it depends on what about the function you know. Now, in the unlikely event that your function happens to be written out as a set of ordered pairs or as a drawing of a map, what you can do is you can simply say, well, a function needs to have all the first entries to be unique. A one-to-one function not only has all the first entries unique, but also all the second entries. All right, so here, these two entries are not unique. You have the same second entry for both of these. And so even though this is a function, this is not one-to-one. This one, on the other hand, is. Every x value ties to just one y value, and every y value ties to every x value. That's where the name one-to-one comes from. One of these pairs to one of these. One and only one. Okay? Now, that's not likely to happen that you have a drawing or that you have a set of ordered pairs. Usually what you have is either a graph or an equation that defines your function. So let's take a look at how to do that. Is this the graph of a one-to-one function? And let's take a look at a few different graphs. Here, let's not worry about the equation just yet. We'll do that in the next part. Here, let's just take a look at some visuals. Let's say someone went through and built these graphs from some equation. We don't really worry about what the equation is. We just need to know what the graph looks like. Okay? So let's take this one. Let's take this one. And we'll take this one. Okay? So first of all, is this a one-to-one function? Well, like we said before, if it's not a function, we're not going to worry about them. So the first thing we want to do is we want to check, is it a function in the first place? One way that we saw to check whether or not something is a function is with the vertical line test. Here, because you have vertical lines that can cross through this graph multiple times, this violates the vertical line test. Because I can think of a vertical line which crosses this graph more than once, that means that, well, I have the same x value occurring twice. Oh, but if the same first entry occurs twice, then that's not a function. So here this is not a function. And if it's not a function, well, then it can't be a one-to-one function. We just don't worry about this anymore. It's not a function. It fails the vertical line test. Now, this one is a function because every vertical line you can imagine will cross no more than once. All right? If you put a vertical line anywhere through this graph, it only crosses at one point. But now, just because it's a function does not mean it's one-to-one. A function should not repeat its first entry. We do that by checking the vertical line. A one-to-one function should not repeat its second entry. Well, notice right here, if I have this line crossing through that graph, even though these are two different points, they have the same distance away from this axis, which means the second entry would be the same. This would be a point like 2 comma 3, and this over here would be a point like 2 comma negative 3. So even though I have two different points, they share the same second entry. So notice this horizontal line tells us that even though this is a function, it is not one-to-one, because you have two different points that share the same share the same second entry. This would be negative 2 comma 3 and 2 comma 3. So this is a function, but it is not one-to-one. And it is not one-to-one because I have a horizontal line that crosses through the graph more than once. This is called the horizontal line test. It's just like the vertical line test, but instead of testing whether or not it's a function, it tests whether or not the function that you have is one-to-one. So this is not one-to-one because it fails the horizontal line test. All right. Now this one, well, this one passes both tests. Every vertical line you can think of crosses no more than once. And here, every horizontal line you can think of, again, crosses no more than once. So here, this is a one-to-one function. Because it passes both the vertical and the horizontal line tests. All right. So let's actually write that down for us. What is the horizontal line test? The horizontal line test, much like the vertical line test, uses a single type of line to test whether or not a function is, in this case, one-to-one. If any horizontal line crosses the graph of a function more than once, that function is not one-to-one. But then, as we saw a moment ago, if a function is not one-to-one, then that means it's not reversible. Here, I may be able to uniquely say, okay, I know what my element in my domain is that ties to an element in my range, but I can't go backwards because there are some elements in my range that I don't know exactly what they pair with in my domain. So if this horizontal line test confirms that something is not one-to-one, that also confirms that it is not invertible. So we can say that, well, then we can say that if a function is one-to-one, then it has an inverse. And the other way around is true. If a function has an inverse, it is one-to-one. Whenever you have a statement like this, that's true in both directions. If this is true, then that's true. But if that's true, then this is true. It's the same statement in both directions. We can usually tie this together with a single statement. The way we read this is as follows. If you have both statements together, they can be read as a single statement. A function has an inverse if and only if it is one-to-one. Anytime you see a statement like this, if and only if, that means it's true in both directions. This one makes that one true, and that one makes this one true. All right? So we have that statement. If a function has a function has an inverse, if and only if it is one-to-one. So now let's take a look at what we mean by an inverse. Now, of course, we say that it's reversing a function, but what does that mean exactly? How does that work? Well, let's take a look at another example to see that in action. The question is, are these functions inverses. So let's take a couple of functions. Let's say f of x equals 6 over x plus 2. And let's say we have another function, we'll call that one g. And let's say g is equal to 6 minus 2x over x. Okay, so are these functions inverses? Well, how can we tell? Well, for this, we're going to use a definition. So here, let me go ahead and write the definition down here. Give myself some space to work further up. Definition. Let f and g be functions. If the composition of f with g is equal to the composition of g with f is equal to x, then f and g are said to be inverses. So the definition of two inverse functions is if their composition gives you just x. What does that mean exactly? Well, we're going to use this example to hash that out. So first of all, let's compose these. Let's plug one into the other. So here, let's find f of g of x. All right. Remember how composition works? Well, if we're saying f of g, that means, well, normally we plug something into f. Well, this time what we're going to plug into f is not a number, but this function over here. Okay, that's fine. So here that's going to give me f of, and now instead of plugging in a number right here, I'm going to plug in this whole thing. I'm going to take 6 minus 2x over x, like that. And now remember what f is. F is a function that says, whatever you plug into me, I'm going to add 2 to it, and then make it the denominator underneath the number 6. Okay, well, here's what I plugged in. So I'm going to take 6 minus 2x over x. I'm going to add 2 to that, and I'm going to put that underneath the number 6. All right? So all we've done is we've taken this and plugged it in right there. We took this and plugged it in right there. All right? So now let's simplify this thing. Let's see what happens after we've plugged everything in. Here we can add these if we give them a common denominator. So here, let me go ahead and multiply top and bottom by x. That way, they have a common denominator. So when I add these together, notice that I have 6 minus 2x and then plus 2x. Well, then these go away, and I'm just left with the number 6 over a common denominator of x. Okay? All right, well now, dividing by a fraction is the same as multiplying by the reciprocal. So if I'm going to take 6 and I'm going to divide by 6 over x, that's the same as multiplying by x over 6. And since now these two divide away, I'm left with just x. So if I compose these, I get just x. Well, what happens if I compose them the other way? Well, let's see. Let's say instead of saying f of g of x, let's say we said g of f of x. Okay, well that's going to be g of, and here we're going to plug into g, we're going to plug in f, which is 6 over x plus 2. F goes in here. Now g is a function that says whatever you plug into me is going to go there and there. So let's go ahead and put this 6 over x plus 2 there and there. So it's going to give us 6 minus double some amount over that same sum amount. That's 6 minus 2 something over something. And now that something is going to be this 6 over x plus 2. And same thing right here, this will be 6 over x plus 2. So now we can simplify. If we take negative 2 times 6, this simplifies to give us 6 minus 12 over x plus 2 over 6 over x plus 2. I can combine these by giving them a common denominator. If I multiply the top by x plus 2 and the bottom by x plus 2, these now have a common denominator. And so now this whole thing will become, well, let's see, 6x plus 12. All right, 6 times x is 6x. 6 times 2 is plus 12 over x plus 2 minus 12 over x plus 2. This one hasn't changed yet. And all of that is over 6 over x plus 2. And as complicated as that looks, a bunch of stuff is about to go away. Look, 12 minus 12 is 0. So this will give me just 6x over x plus 2 over 6 over x plus 2. But now I can divide 6 into 6 and x plus 2 into x plus 2, which gives me just my x. That's the only thing left. So notice here, it doesn't matter which way we composed. F of g or g of f gives me x either way. By definition, f and g are functions. Okay, well, we just start off with two functions. If their composition is, both the compositions are equal to x, then these functions are inverses. And that's exactly what we have. So here are the function inverses. Yes, yes, they are, because their compositions both gave us x. Okay? So now what does this mean, though? I mean, yeah, by my definition, I can tell that these two functions are inverses. But, like, what does that label mean? Well, by definition, it means this. But let's go ahead and give another way of talking about what inverses are. Let's use these same two functions. After all, we just confirmed that they are inverses. So let's see what happens here. I'm going to do something with this function. I'm just going to go ahead and plug in a number. It doesn't really matter what number I plug in, but I'm going to plug in the number 4. Let's say plug in the number 4. So let's plug in f of 4. And now you say, well, why did you plug in 4? I just picked the number. I wanted something simple, so I just picked a small whole number. It doesn't matter what number you pick. So here, f of 4, well, let's see. That's going to be 6 over 4 plus 2, which is 6 over 6, which is 1. You say, yeah, so what? Well, now, that's the result of plugging 4 into f. But now, let's do something with g. You say, oh, so you're going to plug what? You're going to plug 4 into g also? No. Let's see what happens if I plug in the number 1 right here. The results of plugging in 4 right here gave me 1. Okay, so now let me take that 1 and plug it in here. All right, well, that's going to be 6 minus 2 times 1 over 1. All right, these x's are becoming 1. So that's going to give me 6 minus, well, 2 times 1 is still just 2 over 1. And 6 minus 2 is going to give me 4 over 1, which is just the number 4. But notice what happens. If I start with a number, f changes it. But then g changes it back. If I started with 4, I end up with 4. So if I have the number 4 here in my domain of my original function f, that means that I get 1 in the range of f. So here, to go from 4 to 1, I would use the function f. But now to go from 1 back to 4, I would use the function g. One function undoes whatever the other one does. That's a really common way for people to think about an inverse. The inverse of a function is whatever undoes what the original function did. If the original function turns 4 into 1, then the inverse function will take that 1 and turn it back into the 4. Right? It doesn't work with just numbers. It can work with anything. If you plug anything into f, as long as it's in the domain, it'll change it, and g will change it right back to what we started from. That's what the definition of this is saying. If I plug one into the other, and it doesn't matter which order I plug them into, here, f of g of x, these two undo each other, and you're back with whatever x you started with. If you plug f into g or g into f, they undo each other, and you're left with just the original x that you started with. Here, I started with a 4. The two functions undid each other, and I end up with, again, just that original 4. Right, so that's how we can confirm whether or not two functions are inverses. But what if I don't have those two functions? What if I just have a function, and I'm trying to figure out what its inverse is? So that's our next example. What we want to do is we want to say, okay, example, find the inverse of the function f of x equals to, and here we're going to start off with something like 3 minus 2x over 5. All right. All right. First of all, to find an inverse, remember, we're not guaranteed to have an inverse. So the first thing you need to do is check if this is a one-to-one function. If you have its graph, well, then you can check it by looking at the graph, as we saw in a previous example. But if you don't have a graph, your options are you can make a graph, which we've seen can take a little bit of a while depending on what the function is. Or the other thing we can do is we can go back to the definition of one-to-one. So here, first, check if f is one-to-one. Now note, some of the problems in your homework will begin by saying, find the inverse of this one-to-one function. If that's the case, they're telling you, hey, this is one-to-one, so you wouldn't need to check that. But if they don't tell you it's one-to-one, then that is something you need to check, because not every function is one-to-one, which means not every function will have an inverse. All right. By definition, a function is one-to-one if, right here, if for every a and b in the domain of f, you have such that a not equal to b implies that f of a is not equal to f of b. All right? So what we're going to do is we're going to take that and we're going to find what happens if I plug in two different numbers right here. Now you might say, well, which number should I plug in? Which ones do I pick? Well, that's the thing. We don't want to depend on luck. We don't want to depend on, oh, we chose just the right two numbers. So instead of choosing specific numbers, we're going to choose two arbitrary numbers. When we say arbitrary numbers, we mean we're going to pick two different variables and have them represent two different numbers. Here's how it'll look. Let's find f of a. Well, that's pretty simple, because after all, the way function notation works, if you're replacing that x with an a, that means you're replacing that x with an a. So I get 3 minus 2a over 5. And that's it. That's what f of a is. I can do something similar to find f of b. Let's find f of b, and that's equal to 3 minus 2b over 5. Okay. What I want to do now is I want to say, okay, let's say that these two are equal to each other. If that forces a and b to equal to each other, then that satisfies our definition of one-to-one. But if this can equal to that, but a and b can be different, well, then that would not be one-to-one. So let's go ahead and check that out. Here we're going to say, okay, let's take f of a and set it equal to f of b. So set f of a equal to f of b. All right, and the way that would look is we would take that 3 minus 2a over 5, and we would set it equal to the 3 minus 2b over 5. And now what we want to do is we want to simplify. We want to simplify each of these so that you isolate your variables, or at least that's the goal. That's what we're trying to do. If we can't isolate the variables, if we can't get a is equal to b, well, then these two functions, then that means that this function is not one-to-one. All right, so let's give this a try. I could multiply both sides by 5, so that goes away. Those divide out. And I'm left with 3 minus 2a equals 3 minus 2b. I could add 3 to both sides. And those I could subtract 3 from both sides, couldn't I? And those subtract away. 3 minus 3 will give me 0. And this will leave me just minus 2a is equal to minus 2b. And finally, I could say I'm going to divide both sides by negative 2. And those two numbers divide away. So here we're left with a is equal to b. So what that means is if f at a equals to f at b, that forces a to equal to b. If a is not equal to b, well, then that would mean that this couldn't have been true. But that's what our definition is. Our definition says if a is not equal to b, that would force f at a to not equal f at b. So there we go. So this tells us that, yes, this function is one-to-one. And because it's one-to-one, that means it is invertible. If it was not one-to-one, we would just stop the problem right here, and the answer would be this function does not have an inverse. All right? But since it does have an inverse, because it is one-to-one, then we can continue. Okay. So now what we want to do is we want to look at this and first of all, we're going to change f of x and we're going to write it as y. That's technically not necessary, but it does make the next few steps a little simpler, a little easier to see. If you leave it as f of x, it can get a little bit messy in the notation. So here I'm going to replace this with a y. And now what we're going to do is we're going to say, okay, here's our function. What an inverse function does is it reverses all of the roles of the domain in the range. All right? Normally, f goes from here to here, but g goes backwards. So normally you go from x to y, but here you're going from y back to x. We're going to take that literally when we find the inverse. We're going to take the element which represents elements of the domain. You're going to take your x, and you're going to take what represents elements of your range. You're going to take your y, and you're just going to flip them. So here is your original function. The inverse is going to be x equals to 3 minus 2y over 5. But now that's not how you write a function, right? When we write a function, our function notation always has us isolate the dependent variable. In other words, we isolate the y. So here, we're going to go ahead and isolate this variable. We're going to multiply both sides by 5. Gives us 5x equals 3 minus 2y. We can now subtract 3 from both sides. So that'll give me 5x minus 3 is equal to negative 2y. And finally, I can divide both sides here by a negative 2. And that'll isolate my y, which is now equal to, oh, let's see here. I have a negative over a negative, that's a positive. And a positive over a negative, that's now a negative. And it looks like that. Finally, this function is not the same as our original function. Notice they have some similarities, certainly, but they are not the same. So here, we want to distinguish this function from this function. So we're not going to call them the same thing. Right? This one's called f. We wouldn't call this one f. But we also don't want to set them too far apart. We don't want these to be thought of as two completely different functions. After all, there's a relationship between these. This one is the inverse of that one. So instead of giving it a totally different name and calling it g of x or h of x or some other letter, what we do is we use the following. This is called the inverse notation. So the function f will have an inverse, which is denoted this way. We're going to write the f, which is the name of the original function, and now we're going to put a little minus 1 right here. So instead of f of x, we're going to write f with that little minus 1 of x. This is read as f inverse of x. This one is read as f of x. This one is read as f inverse of x. So f inverse of x is the function that flips this one, that inverts this one. And it is equal to 3 minus 5x over 2. And there we go. There's our answer. That is the inverse of that function. All right, so now let's take a look at this example. Find the equation for the inverse of the one-to-one function f of x equals x minus 5 over x plus 1. Now notice here, this one you're told it is a one-to-one function. So we can skip that part. We don't need to confirm this is one-to-one. We're already given that information. So pause the video and give this a try. See if you can find the inverse of f of x. Once you get to a part where you're comfortable, go ahead and restart the video and we'll walk through it together. All right, so let's go through this now. We have f of x equals x minus 5 over x plus 1. Let's begin by replacing that f of x with a y. All right, now, if this is my original function, the inverse function reverses the roles of the domain in the range. So here we can represent that by saying all y's, we're going to call them x, and all these x's, we're going to call them y's. Just like this. Now, this is the inverse function. But we don't leave it that way, because function notation has us writing things with respect to the independent variable. We're trying to isolate y with respect to x. So now we're going to go ahead and isolate y. Here, if we multiply both sides by our denominator, that makes things a lot simpler, because now we don't have to deal with a denominator at all. So here I'm going to multiply both sides by y plus 1, and this will give me x times y, well that's xy, and x times 1, well, that's just x, and that's going to equal to y minus 5. Now once again, I'm trying to isolate my y. I want y equals to something in terms of x. So let me get all my y's together. Let me go ahead and subtract my y over to this side. And while I'm at it, let me subtract my x over to this side. The goal is to get everything with a y on one side, everything without a y on the other side. Like this. So this will give me xy minus y equals to negative 5 minus x. Right, these are over here together. Now you notice the y is common to both of these terms. And because it's a common factor to my terms, I can factor it out. I can write this as y times x minus 1 equals negative 5 minus x. And finally, we're just about done. We're trying to get that y by itself. So let's divide away the x minus 1 from both sides of the equation to isolate our y. And so now we've isolated y equals to negative 5 minus x over x minus 1, and that makes us happy. Because now we have our inverse of our original function. Notice it is very similar to our original function, but it's definitely not the same. So here we're going to give this the inverse notation. We're going to write this in the inverse notation. And we're going to write this as, well, if our original function is called f, we'll call this one f inverse. So f inverse of x is equal to negative 5 minus x over x minus 1. And that is our end result. All right? Now, if you pay attention to one of our earlier examples, there may be something that's bothering you. Back over here, we said, all right, that's not a function. Okay, fine. That's a function and it's 1-to-1, so we should be able to find its inverse. Here we said it's a function, but it's not 1-to-1 because it fails the vertical line test. But then we said that a function could only be inverted if it was 1-to-1. Right? A function has an inverse if and only if it's 1-to-1. If you put those two things together, it gives you something a little strange. Because, okay, a function, if it's not 1-to-1, it's not invertible. Okay, fine. But that's not 1-to-1. Okay, so that means it doesn't have an inverse. And yet we recognize this. This is a parabola. It's y equals x squared, or y equals 2x squared, or 1/3 x squared, or something like that. It's a quadratic. It's a parabola. But in chapter 2, we defined the parent functions, and one of our parent functions that we defined was the square root. So what's a square root if it's not the inverse of a parabola? After all, this is y equals x squared, or something like that. But if that's not invertible, where does the square root come from? So let's go and take a look at that. We can take a inverse of a function. We just have to be a little bit more careful. So let's take a look more closely at that function. F of x equals 2x squared. All right, well, we know what the parent function of that looks like. And we have a pretty good bit of experience with its graph. It's a parabola that looks like this. All right, now, that is not a 1-to-1 function. It is a function, but it's not 1-to-1 because, look, there are several horizontal lines which cross through the graph more than once. So this is not invertible. You say, well, then where does the square root come from? How did I invert this in the first place? Well, this graph as it's written is not invertible. But what we can do is we can cut off a piece of it that is. Here we can say, all right, consider another function that is related. Let's consider f of x equals x squared. And you say, well, that's the same function. Okay, but now let's consider f of x equals x squared only for whenever x is greater than or equal to 0. That would give us only the right half of our parabola. That would give us just this. Okay, so now that piece is 1-to-1. So now that I could invert. After all, we could say, okay, this right here, y equals x squared. And so, if we have this as our original function, keeping in mind that we only want x to be greater than or equal to 0, then here we have x equals y squared. That's the inverse of the original function. Now I can take the square root of both sides. And you say, okay, well then take the square root of both sides and that'll be plus or minus, right? No, it wouldn't be plus or minus, because notice on our graph we've only taken all points where x and y are both positive. Here you're in the first quadrant, and in the first quadrant x is positive and y is positive. So here, when we take the square root, we would be violating our domain and our range if we included any negative values. So we can't have plus or minus. It's strictly plus. So here, this would give us y is now by itself is equal to the square root of x. Right? That's where y equals square root of x comes from. It's the inverse not of the whole parabola, but of just the right side. So here we can write this as f inverse of x equals the square root of x. And here we only have the square root of x for whenever x is positive, right? For whenever x is greater than or equal to 0. You say, all right, so wait, what about that plus or minus thing though? If we only consider the positive square root, what happened to the negative square root? Well, that's the other half. Other half of what? Well, remember, we have a parabola. We only considered the right half. Let's consider now the left half. Let's say I had f of x equals x squared, but now I only want it for whenever x is greater than, let's do it the other way. Let's say I only want it for whenever x is less than 0. So now that would be just the left-hand side of my parabola. That looks something like this. Okay, so now if I were trying to invert this, I could say y equals x squared. And again, keep in mind that there's a restriction. X should be negative. Here, this would be my original function. But now my inverse would be x equals y squared. I can now isolate my y, and that's going to give me the square root of both sides. Just like that. But notice here, this should be a negative. So when I take a square root, if I take the positive square root, that'll give me a positive. And I'm not supposed to get a positive. This is supposed to be negative. So here, I need to be taking the negative root of both sides, like that. So this will give me the y now by itself is equal to the negative square root of x, which of course I can write in my function notation. I can write that as f inverse of x equals the square root of x. But now it's the negative of that. Now, look at those graphs. This is the positive half of the parabola. If I invert just that one, I get the positive square root of x. And we know what that looks like. We have a parent function that we saw all the way back in chapter 2. It looks something like this. All right, cool. But now look at this one. Here I have a function, and the inverse is not the regular square root, it's the negative square root. Well, again, thinking back to chapter 2, these two are the same function, but this one's been multiplied by a negative. So you would take your parent function and reflect upside down. When your negative is on the outside, it's a reflection across the x-axis. So here, instead of having this as the inverse, I would have the other half. I would have this bottom part as my inverse. This shows me a couple of things. First of all, it shows me how I can possibly invert things that would otherwise not be invertible. For those of you who go on to trigonometry, this will be useful when we look at periodic functions. Periodic functions are not one-to-one functions, but if you cut them up into smaller pieces, you can find the inverses of those smaller pieces. And although that's not the inverse of the function overall, it's it's useful and certainly better than nothing. The other thing it shows you is that, well, there's a relationship between the graphs of a function and its inverse. I suppose before I continue, I should finish labeling these. So here we had x is greater than 0. Same thing over here. We're going to have x is greater than or equal to 0. Oh, I suppose that should just be greater than. But now our y value is what's different. Here, we took a positive square root, so y was also positive. But here, we're taking a negative square root, which means y would be negative. Like that. And that's just giving us the domain and range of the inverse function. So here we have the graph of this one. And notice the domain does match up. Everything is to the right and down. And here, the domain and range also match up. Everything's to the right and up. So now, I was saying that we have a relationship between the graph of a function and the graph of its inverse. This relationship will be a wonderfully useful shortcut in coming sections and in coming chapters, not to mention in other classes for those of you who go on past college algebra to take trigonometry or calculus. That relationship is as follows. Once we draw it, it's going to seem pretty much in keeping with everything we've done so far. So notice here, I can draw this diagonal line, and this diagonal line acts as a mirror. Anything that touches this diagonal line, any part of my original function that touches this diagonal line, the inverse also touches that diagonal line. Here, here, and here. But anything that doesn't touch that diagonal line, notice it's being reflected. This blue part is being reflected above the line, and this blue part is being reflected below the line. This line acts as a mirror where the original function and the inverse of that function are reflected across that line. Now that line is the line y equals to x. Y equals to x. This is in keeping with just about everything else we've seen, because notice, if you have the original function y equals to a function of x, the inverse has x as a function of y. Going back to our very first illustration, whenever you have an inverse, what you're doing is you're just reversing the roles of the domain and the range. Right? Normally your function goes from here to here, but your inverse takes you from here back to here. Oh, well then that just means my x's and my y's are flipped. But you know, if you're flipping x and y, that doesn't affect anything on this line, because on this line, x is equal to y. And if I have x is equal to y and I flip it, well, I get y is equal to x. But that's exactly the same thing. X equals to y is the same as y equals to x. So anything on this line remains the same. But anything that's off of this line is now reflected. So if, for example, this was the point 9, 3, I can reflect it, and now that's the point 3, 9, like that, a reflection. So every time you have the graph of a function and its inverse, they are reflected across the line x equals to y. So here, note the graph of f and the graph of f inverse, and it doesn't matter what f or f inverse are as long as they're inverses of each other. The graph of f and the graph of f inverse are mirrored across the line y equals to x. Right. So as a quick example of that, let's say you have a couple of graphs. Say we have this one here. Let's say we have this one here. And let's say we have this one here. All of these are functions, and in fact, they're all one-to-one. So if you were going to graph the inverse of these functions, you would simply reflect them across this line, x equals to y, the diagonal line with a slope of 1. So to graph, this would be reflected down here. It's a mirror image. Here, this point touches the diagonal line, which means that on the inverse, that point would also touch the diagonal line. But now everything below here is now reflected up above here. Everything above here is now reflected down below here. So if the one in blue is the function f, the one in red is f inverse. If the one in blue is g, the one in red is g inverse. And likewise here, notice this blue graph touches the diagonal line at 3 different places. Okay, so then the inverse will also touch that diagonal line at 3 different places. But now this stuff down here would be reflected up. This, which goes very quickly up, would now be reflected to go very slowly up. It would flatten out a lot. Here, this part that's above the line would now be reflected below the line. And now this goes down very sharply, but reflecting it would now have it go down very flatly, just like this. So this graph in red would be the inverse of the function who's graphed in blue. And that's the end of our section.